Okay, so let's review one more example in section 4.2. Okay, so it's the last example in section 4.2. So we have a linear transformation sending from R3 to R3. And it's defined by this way. You will send the vector x1, x2, x3 to first one is x1 plus s2. Second one is s2 plus s3, and s3 plus s1. This one. And we consider several bases. First of all, it's a standard basis. So it's 1, 0, 0, 0, 1, 0, 0, 0, 1. And we call it E1, E2, E3. And we have a basis F, and it's denoted by 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, and denoted by U1, U2, U3. And another basis H is 1, 0, 1, 0, 1, negative 1, 0, 1, negative 1, and 1, negative 1, 0. And we denote it by B1, B2, B3. And all of them, once you check the determinant, all of them are non-zero. So all of them are bases of R3. So we have two questions. One is to find the standard representation of error. And it means that we want to figure out standard representation. It means that we want to figure out this one for our formula, LE, this one. And yeah, and I will explain the detail, okay? And it's for its diversion, it means that it satisfies this equation, Lx equals standard representation if we denote by A, it satisfies this equation for its definition. The matrix A is a standard representation of error, means that it satisfies this equation for any x. And another one is that we want to find general case, we want to find matrix representation of error with respect to, it's the abbreviation of with respect to order basis, F and H. Okay, so if we say F and its matrix representation of error with respect to order basis F and H, means that this one, the matrix representation of error with respect to this basis, it means that this one, or the notation is this one, error, FH, and it means that it satisfies this equation, error of V equals this one, it satisfies this equation. If we denote this one, VF, it satisfies this equation. And this matrix, we call it matrix representation of error with respect to order basis F and H. Okay, and here you could see that, so for the vector V in R3, so originally the map, I write down here, it's the map R3 F to R3 H, the map error. Originally we have the coordinate vector with respect to the basis F. And here we can, once we have the map, we consider the vector L of V. But for this vector, we consider its coordinate vector with respect to the basis H. And what's their relationship? Their relationship is that it satisfies this equation for any V. Then for this matrix, we call it matrix representation of error with respect to order basis F and H. This this one. This one. Okay, so first of all, let's consider first question. So for the first question, standard representation, its definition is satisfied this one. But for our formula, just consider LE is our result. Just consider LE is our result. So LE is this one. This notation, it means that E is the basis of these three sets. So it means that it's L100, L010, L001. These three vectors. So first vector L100, once you plug in the value 100, you will get 1 plus 0, 0 plus 0, 0 plus 1 in first column. And second column is 0 plus 1, 1 plus 0, 0 plus 0. Second column. And the last column is 0 plus 0, 0 plus 1, and 1 plus 0. This one. So finally, it's equal to 101, 110, 011. This one. So it's what we want. It's the standard representation of error. And actually, you could check it. I mean, for this matrix, if we denote by A, you could check it. For the matrix 101, 110, 011, once you consider this one, their product, what will you get? It's our matrix A, X, and then you will get x1 plus x2 in the first coordinate. Second coordinate, x2 plus x3, and then the last coordinate, x1 plus x3. And then it's exactly the map error. So indeed, it's our LX. Okay, so it's the first question for the standard representation. Of error. Okay. Yeah. Okay. So now let's see the general second question: matrix representation of error with respect to order basis F and H. And it satisfies this equation. So, but we have the formula. So here I erase it. I skip this one. Okay. Yeah. So the thing I erase it. And we will use it again. So let me write down this one. Let me erase this part and okay, so it will satisfy this equation. I mean LV H and FH B F, this one. For all we want is to figure out this one. And for our formula, as we say the map, we consider R3. In the domain we use the basis F, and in its range we use the basis H. Then here for our formula is this one. We put the basis H in the left hand side and put LF in right hand side. Yeah. So and what's the notation? What's the notation mean? So first of all, H is these three vectors. So it's 1, 0. So let me write down this one. We have three vectors, and I denote by B1, B2, B3 in first column, second column, third column. And LF means that LU1 in this column, in first column, in right hand side, and L of U2 is in second column in right hand side, and the last one in L of U3, this one. So now let me write down each vector. So it's 1, 0, 1, 0, 1, negative 1, 1, negative 1, 0. So LU1. So let me write down this name. X1, x2, x3 equals x1 plus x2, x2 plus x3, x3 plus x1. So L of U1 is 1 plus 1. So it's 1 plus 1, 1 plus 0, 0 plus 1 in this column. And this one is 1 plus 0, 0 plus 1, 1 plus 1 in this column. current. And the last one is L of U3. U3 is 0, 1, 1. So it's 0 plus 1, 1 plus 1, 1 plus 0. This one. Okay, so let me write down each term. 0, 1, negative 1, 1, negative 1, 0. Let me check it. Yeah. So it's 2, 1, 1, 1, 1, 2, 1, 2, 1. So yeah, we should use this 10 to cancel this 10. So multiply negative 1a to the last row. So you will get 1, 0, 1, 2, 1, 1. So it's 0, 1, negative 1, 1, 1, 2. So it's 0, negative 1, negative 1. 1 subtract 2, negative 1, 2 subtract 1, 1, 1 subtract 1, 0. This one. And use this 10 to cancel this 10. So multiply 1a to the last row. You will get 1, 0, 1, 2, 1, 1, 0, 1, negative 1, 1, 1, 2. Their sum. 0, 0, negative 2, 0, 2, 2. This one. Okay, so here what we want to do is to lay the identity and to check right hand side is matrix. So we should multiply negative 1 here. Then you will get this 1, 1, 0, 1, 0, 1, negative 1, 0, 0, 1. And it's 2, 1, 1, 1, 1, 2, 0, multiply negative 2, so it's negative 1, negative 1. Yeah. The last step, use this 1 to cancel them. So multiply 1a to the second row, and then multiply negative 1a to first row. Then finally, left hand side is 1, 0, 0, 0, 1, 0, 0, 0, 1. It's identity. Right hand side, the last row is 0, negative 1, negative 1. And their sum, so it's 1, 0, 1. And then 1 subtract 1 is 0, 2 subtract 0 is 2, 1 plus 1 is 2, 1 plus 1 is 2. So let me check it. Yeah. So finally, what we want. Actually, it's what we want. It's the identity, and it's what we want. And actually, it's exactly the matrix, the product of H inverse LF. What we want to figure out is their product, H inverse LF. So of course, you know the matrix H is this guy. You know the matrix, okay, H is this one, LF is this one. So of course, you also could figure out its inverse and consider the product of H inverse and LF. Consider the product directly. Otherwise, you also could use this way to figure out their product, and it's the solution. It's our solution. It's the matrix representation. Of L with respect to order basis F and H. Okay, yeah. So it's the example we explain one more example for you in section 4.2. That's all.